Dear students, I, Mr. Vishal Shah, Assistant Professor, Krishna Institute of Pharmacy, Karad, once again welcome you all to this session of Pharmaceutical Organic Chemistry. In this video, we are going to continue with the next part of the Baeyers strain theory. In previous video, we have discussed what are the different assumptions that Bayer has proposed, and on the basis of these assumptions, he has put forth a theory which is also known as the angle strain theory. This Bayer strain theory gives us information about the stability and the reactivity of cycloalkanes. So in this video we will be going to cover the role of heat of combustion study, which will prove the whatever the certain things that Bayer has proposed regarding the stability as well as the reactivity of cycloalkanes. And also in next part we will see the advantages, disadvantages of this Bayer strain theory. So let's begin with our today's session. Before starting our today's session, just we will see what are the learning outcomes of this session. So after this session, students will be able to explain Bayer strain theory, explain advantages as well as the disadvantages, means limitations of Bayer strain theory. Also to understand role of heat of combustion to study the stability of cycloalkanes. First we will discuss about the heat of combustion, what is the meaning of heat of combustion and how it is helpful to give us idea related to the stability of the cycloalkanes. Now, what is the meaning of heat of combustion? Heat of combustion will give us an idea about the relative stability of cycloalkanes. Now, what is the meaning of heat of combustion? The amount of heat that is evolved when 1 mole of a compound is burned in carbon dioxide and water. And this, the heat that is evolved is known as heat of combustion. Means if we take 1 mole of any particular molecule, and if we burn that 1 mole of a molecule into the environment of carbon dioxide and water, then the whatever the heat that is evolved, that heat evolved is known as the heat of combustion. Heat of combustion is important property to know the stability and other valuable information. So it is important to know the heat of combustion study because it will give us an idea about the stability of these cycloalkanes. The information from heat of combustion is important to understand the Bayer's theory as well as its limitations. Means whatever the certain things or the assumptions that Bayer has proposed, whether these assumptions are correct or not, or whatever the things that Bayer has proposed, whether these things are correct or incorrect, that could be understood with the help of this study, that is the heat of combustion study. Now we know that for open chain compound like alkanes, heat of combustion for a CH2 group, that is the methylene group, is 157.4 kilocalorie per mole. Means if the 1 mole of any alkane is studied with the help of the heat of combustion study, and the whatever the CH2 group that is present in that alkane, that will evolve the 157.4 kilocalorie per mole. Means that much energy is eliminated when one CH2 group is heated in presence or burned in presence of carbon dioxide and the water. Now if we consider the cycloalkanes, depending upon the ring size of that particular molecule, heat of combustion per CH2 group is different, and this is depicted in this particular table. Here you can see on this left side column I have mentioned the ring size, and here heat of combustion per CH2 molecule that is present in the kilocalorie per mole. Suppose a ring size, that is the cyclopropane is having 3 mole of CH2. So 1 CH2 when burned into carbon dioxide and water, it will evolve 166.6 kilocalorie per mole. Similarly, for a ring size 4, if that particular molecule is burnt for the study of heat of combustion, then one CH2 molecule will evolve the 164.0 kilocalorie per mole. Similarly, if ring size is 5, for example cyclopentane, then heat of combustion per CH2 molecule will be 158.7. For a ring size of 6, that will be having a 157.4. Similarly, if ring size of that particular cycloalkane is 7, then heat of combustion or heat that is evolved per CH2 would be 158.3 kilocalorie per mole. Ring size of 8, then heat of combustion or that is heat that is evolved per CH2 in kilocalorie per mole will be 158.6. Similarly for 9-membered ring as well as 10-membered ring. In this way, these are the various values when the 1 mole of that particular CH2 group is undergoing the heat of combustion study. Now just we will be interested in this particular 3 to 4 values, where the ring size is 3 for cyclopropane, then for cyclobutane it's a 164, for cyclopentane it's a 158, and for cyclohexane it's 157.4. Means here you can see that when the CH2 groups that are present in the cyclopropane, when they are undergoing the heat of combustion, they evolve more amount of energy. So cyclopropane is having more amount of energy within it. Now how heat of combustion of total molecule is calculated? Means for example for CH, here whatever the chart that we have seen, it is only related to CH2 group. But as we know, so many number of CH2 groups are present depending upon the ring size. So for whole molecule, how to calculate the heat of combustion? This can be calculated by using formula. Heat of combustion of that particular molecule is equal to number of carbon atoms in that ring. That is meaning the ring size, that is the 3, 4, 5, 6. Then heat of combustion of that ring per CH2 minus heat of combustion of normal alkane per CH2. Now we know, first we will discuss this regarding the calculation of heat of combustion for cyclopropane. The number of carbon in the cyclopropane is equal to 3. As we know, the ring size of that particular cyclopropane is 3. Then observed heat of combustion for 3-membered ring is equal to 166 kilocalorie per mole. Now we know for heat of combustion for open chain CH2 group is 157.4. If we put these 3 values into this particular formula, we can get the heat of combustion of the cyclopropane. Therefore, heat of combustion of cyclopropane is calculated as 3 into 166.6 minus 157.4, that is equal to 27 kilocalorie per mole. Means if 1 mole of cyclopropane is burned in the environment of carbon dioxide and water, it will evolve 27 kilocalorie per mole. Similarly, we can calculate the heat of combustion for cyclobutane and cyclopentane. For cyclobutane it is 26.4 and for cyclopentane it's a 6.5 kilocalorie per mole respectively. So here we can see how to calculate the heat of combustion for the cyclobutane. Here you can see, as we know, the ring size of cyclobutane is 4. So number of carbon atoms in the cyclobutane are 4. Observed heat of combustion for the 4-membered ring, as we know from the chart value, it's 164.0 kilocalorie per mole. Then we know the observed heat of combustion for the open chain CH2 group, that is equal to 157.4. Now therefore heat of combustion for cyclopropane is equal to 4. Sorry, here by mistake I have placed 3. 4 into 164.0 minus 157.4, that is equal to 26.4 kilocalorie per mole. So when cyclopropane undergoes heat of combustion, it will evolve more amount of energy, while cyclobutane when undergo heat of combustion, it will evolve less amount of energy. So more amount of energy is stored in that cyclopropane, and that's why its stability is less. While similarly, heat of combustion for cyclopentane is calculated, and which can be calculated in cyclopentane number of carbon atoms are 5. Then by using again the values related to the heat of combustion for CH2 in a ring as well as for open chain compound, we can calculate, and that value becomes 6.5 kilocalorie per mole. Now upon examination of this data, that is the values that are obtained for cyclopropane, cyclobutane as well as the cyclopentane, it can be seen that cyclopropane and cyclobutane evolve more amount of energy per CH2 group than its open chain compound, and that may be the reason for the instability and their tendency to undergo the chain opening reactions easily. So cyclopropane and cyclobutane are more unstable because they are having, or they evolve the more amount of energy per CH2. But cyclopentane, cyclohexane, they evolve very less amount of energy per CH2 group as compared to the open chain compound, and that's why this is the reason, that's why these particular compounds does not undergo chain opening reactions that much very easily. So that is the difference, or the stability of that particular these cycloalkanes can also be confirmed with the help of this heat of combustion study. So certain things that Bayer has proposed were right, which can be confirmed with the help of this heat of combustion study, where cyclopropane and cyclobutane are least stable as compared to the cyclopentane as well as the cyclohexane. But Bayer has proposed that cyclopentane is more stable as compared to the cyclohexane, but this is not true. Heat of combustion value for cyclopropane and cyclobutane are higher than open chain compound by 9.2 and the 7.0 kilocalorie per mole respectively, and due to which they are highly unstable. According to this data, cyclopropane is less stable as compared to the cyclobutane. Means heat of combustion study also confirms that cyclopropane is less stable as compared to the cyclobutane. For this ring system, Bayer's theory was correct. As I said, for stability of cyclopropane and cyclobutane, whatever the Bayer has proposed, these things were correct. But it is not correct for the cyclopentane and cyclohexane. On observing the data for the cyclopentane, then it can be seen that the value for heat of combustion is higher than open chain compound, where open chain compounds are having 157.4 kilocalorie per mole. The value is much higher than open chain compound for the Bayer's most stable compound, that is the cyclopentane. According to Bayer, cyclopentane is the most stable compound, but for cyclopentane also this heat of combustion is more as compared to the open chain compound, and that's why for other larger ring system the values for heat of combustions are very close to the open chain compound. That indicates the stability of those compounds. If you now calculate the heat of combustion study for the cyclohexane, cycloheptane, cyclooctane, then nonane, for these compounds the heat of combustion values are very closer towards the open chain compound. So it indicates these compounds are more stable, where the Bayer has unable to explain these particular things. Means according to him, cyclopentane is more stable, but practically cyclohexane is more stable as compared to cyclopentane. So it can be confirmed with the help of the heat of combustion study that the certain facts that Bayer has proposed are correct. Here Bayer's theory was incorrect to justify its stability. So thank you. In next video we will see the remaining part of the Bayer strain theory, that is the certain angle orbital pictures of that particular different cycloalkanes. If you have any queries related to the pharmaceutical organic chemistry, then you can contact me on my mail ID shahavishalvi99@gmail.com. And if you like the content of this video, please like my videos, share with your friends, and subscribe to my YouTube channel. Thank you.